So one small announcement. Somebody pointed out correctly that the field trip to Lick was scheduled on homecoming weekend when families will be visiting potentially and other things like that. So I'm looking into rescheduling that, and I'll let you know what we end up being able to sort out. So any questions from last time? Okay. So what we're going to do today is talk about how the understanding of gravity that we developed last time can be used to really understand the formation of the solar system and more generally the formation of stars and planets. Just to remind you, the names of the planets, Jupiter, Uranus, Mars, etc., are actually taken from Roman gods. And so in the ancient times, the mythologies associated with the formation of the solar system and the origin of the solar system were actually intimately related to basically the soap opera of the gods. So battles and conflicts between the gods were central to the notion of how the solar system originated. And so today we're going to try to use our understanding of gravity really and fill in the picture of how the Earth originated. And I'm going to focus on our solar system, but the story that I'm going to tell you is actually more broadly applicable and describes, in general, the formation of stars, planets, and solar systems. So I think it's useful just to summarize briefly some of the salient properties of the solar system that we're actually trying to understand. So not only that there is a central star surrounded by these planets, but there are some very specific properties of the solar system that really are critical clues to how it formed. One of those is that, generally speaking, the planets are on roughly circular orbits. So remember, in general, the orbits of planets are ellipses, kind of elongated circles. But in fact, most of the planets in the solar system are pretty close to circles. So circles are special in that for a circular orbit, the distance between the planet and the star is always the same. So one way to describe how close the orbit is to being a circle is to say how different is the distance between the planet and the sun over its orbit. In the case, and that measures kind of how elongated the orbit is. In the case of the Earth, there's right now only about 2% differences between the Earth and the sun over the course of the Earth's orbit around the sun. We'll see later in the course, though, that this actually changes on very long time scales, hundreds of thousands of years. And that, as Charles alluded to last time, is actually responsible in large part or in significant part for the ice ages. Mercury among the planets is the most extreme in having about 20% differences between the distance between Mercury and the sun. The other kind of very important fact about the planets is that they all roughly orbit in the same plane. They're all in the same kind of pancake or disk-like configuration. They all go around the sun in the same direction. It's not like half the planets go one way, half go the other way. And then something we noted in the second lecture, and we'll come back to towards the end, is that there's a big difference actually in what the planets are made of close to the sun and far away from the sun. Close to the sun, the planets are mostly rock, iron, silicon, oxygen. Far away, the planets are actually more like the sun. The sun is mostly hydrogen and helium. Far away from the sun, the planets are actually more like the sun, mostly hydrogen and helium. Yep. So the question is there a reason why they all spin in the same direction? And that's something we're going to get to today. Exactly. So you can kind of visualize this point, roughly circular orbits, orbiting in the same direction, same plane. You can visualize this by trying to plot the actual orbits of the planets around the sun. So here is the sun. This is the orbits of the inner planets. And then zooming out, this is the orbit of the outer planets. And there's a way of depicting sense of rotation around the sun and sense of rotation of a planet around its axis that's used in this diagram and that we'll use multiple times in the course, which is the way you should think of these arrows is imagine taking your hand and having your fingers go in the direction of the arrow. That's the direction that the planet is actually going around the sun in its orbit. So the arrow here indicates that the planet's orbit is like this, and your thumb is pointing in the direction that's perpendicular to the plane of the orbit.
And this is a right-handed globe, is it?
Yes, so this is biased towards right-handed people. That's exactly right. Okay? So that's, when you see these arrows, that's what they're trying to convey, is what is the direction that things are going. Then these other little arrows here associated with each object, the sun and all the different planets, that actually tells you the direction of the spin of the planet, like the Earth's, right? The one-day period of our rotation about our own axis, not about the sun. So you can see that most of the objects in the solar system spin in the same direction as they orbit. The arrows are pointing up, which by the right-hand rule means that they're spinning themselves around the same axis as they're rotating. There's a couple of interesting exceptions. Venus is actually spinning in the opposite direction that it's orbiting. So it orbits in one direction like this, and it spins on its axis actually in the opposite direction. Pluto is another. Uranus is pretty weird. Uranus is kind of exactly perpendicular. Its spin about its axis is exactly perpendicular to its orbit. And we'll come back to some of these exceptions in a little bit. Yep?
Does that mean for the time of the year when, or your year is the year when it's off to the side of the planet never seems light, and then when it's on the other side, the side that's facing towards the sun?
Yeah, that's basically right. So the question is, doesn't this mean then, because of the way it's spinning, that parts of the planet go through very long periods of no significant light? That's right. And so, in fact, this, as the question anticipated, this issue of exactly the tilt of the spin is very important for the season. So the fact that the Earth has the seasons it does is partially because its spin is tilted a little bit, 23 degrees, relative to its orbit. And we'll see where that comes from a little bit later. So what we want to talk about today is really understand how gravity leads to the formation of stars and planets, why things end up orbiting in disks, rotating in disks, and then we'll talk a little bit about the difference between the inner and the outer planets, and then some of the really dramatic consequences of how the planets actually formed. By bottom up, I mean things start small and then they get bigger, and I'll explain that as we go. So I've shown this picture a few times. This is, again, the picture of our galaxy, the Milky Way galaxy, seen in starlight. Again, disks and spheres, as we talked about last time. There's the disk that the sun is part of. The sun is in the outer part of the disk of the Milky Way. At the center, there's a little sphere of stars. But that basic geometric configuration describes our galaxy. Most of the mass in our galaxy is dark matter, as we'll discuss later in the class. That's about 1 trillion times the mass of our sun in dark matter. The mass of stars in our galaxy is about 50 billion times the mass of the sun. And where do those stars come from? They have formed through time from gas that fills the space between stars in our galaxy. And you can actually take an image of the night sky, not in starlight like this image is, but in the light produced by the gas itself. So this is a picture now of our galaxy, the same projection of the sphere, a picture of our galaxy in the light produced by hydrogen gas. Hydrogen gas emits light in the radio part of the electromagnetic spectrum. So you take a picture with a radio telescope, and you see all the light produced by all the hydrogen gas in our galaxy. And what you notice immediately is that the gas lies mostly in this disk-like configuration. The hydrogen gas that fills the space between stars traces out this disk-like configuration. And now remember, this is like 100,000 light years across, tens of thousands of light years across. If we now zoom into a little patch of this gas, we see something like this image of the Hubble Space Telescope that we also saw in the kind of astronomical census lecture. So this is a zoom in of now a few light years across of the gas that fills the space between stars. And this gas is the gas out of which the solar system and stars and planets form. And that transformation going from this gas to newly formed stars and planets is really a remarkable transformation. And the reason is that the typical density, how much stuff is there in gas filling the space between stars, is just about 1 hydrogen atom per cubic centimeter. So again, visualize a cubic centimeter, right? That's something you can see. And imagine that there's only 1 single atom in that cubic centimeter. That's how rarefied the gas is in the space between stars. And to give you an example, you may have heard about vacuums on Earth where people who do experiments. This is not like vacuum cleaner, right? This is a vacuum in an experiment where in a laboratory, you try to take all of the air out of an experimental apparatus to get rid of the effects of the air in the atmosphere on your experiment. This amount of stuff in space is far more rarefied than the best vacuum that's ever been created on Earth. So this is incredibly tenuous in terms of how much stuff there actually is. And the only reason it adds up to this extraordinarily large amount of stuff, 5 billion times the mass of our sun, is that the galaxy is truly enormous. You take 1 atom per cubic centimeter, you spread it out over tens of thousands of light years, you end up with 5 billion times the mass of our sun. So by comparison, the Earth consists of about 10 to the 23 atoms per cubic centimeter, mostly iron, silicon, things like that. So to form the planets and stars, we have to take this gas and shrink it down and compress it by an enormous amount, from about an atom per cubic centimeter to 10 to the 23 atoms per cubic centimeter. And the way that happens in one word is by gravity. So the schematic picture of how that happens is illustrated here, and then we'll fill this in a little bit. So this is a cloud of gas that's meant to be an artist's conception of the much more impressive Hubble Space Telescope picture there. What happens is that this cloud of gas starts to collapse under its own weight. The gravity of the gas itself pulls everything in on itself. There isn't anything pushing out to stop gravity, so gravity wins. It causes things to collapse in on themselves. As they collapse in, they're rotating, so they can't collapse directly to a point. They start to form this rotationally supported object, a disk. And this disk, then, is the place where the planets form. At the center of this disk is a newly formed star, and in the disk surrounding the star, the planets slowly form. So as time goes on, this disk slowly disappears, and what's left behind are the planets that have formed out of the kind of debris, this disk around the newly formed sun. This process takes a while. It takes tens of millions of years to happen. To take this cloud of gas, collapse it down, form the planets, it's a slow process by human time scales, 10 million years. But remember, the universe is 13.7 billion years old. So on the time scale of the universe, this is actually pretty fast. It's just 10 million years, which is very short compared to the age of the universe. So that's the kind of big picture of how we go from a cloud of gas by gravity collapsing down to form stars and planets. And what we're going to do now is fill in a little bit more of the picture of how that actually happens. Yep?
So to start the gravity collapsing in the gas cloud, there needs to be some sort of outside force.
Yeah, so the question is, to start the process of gas collapsing, does there need to be an outside force kind of pushing in? And the answer really is no, for reasons we'll see in just a second. Yep? Yeah, great question. So when does a cloud like this decide it's going to form stars versus just sitting there happily looking like this? And that's actually the heart of the matter. That's kind of the critical question. And the answer turns out to be a process that we call gravitational runaway. And it's very difficult for me to overemphasize how important this is. So I've tried to illustrate this is important by using every possible tool available to me in PowerPoint. Shading, colors, different colors, purple three-dimensional stuff, right? So this is really the central idea, as you will see, the central idea in our astronomical understanding of origins is this idea of gravitational runaway. And so the idea roughly is the following. In a cloud of gas like this picture here, the amount of stuff at any given point isn't exactly the same everywhere. Some places in the cloud there's a little bit more gas, some places there's a little bit less gas. And so I've illustrated that schematically here by plotting how much gas there is as a function of kind of where you are in the cloud of gas. Some places there's a little more than average, some places there's a little less than average. The regions that just happen by luck to have a little more stuff than average, like this spot or this spot, those regions are a little bit more massive than their surroundings because there's more stuff there. And what we know from gravity is that if you're a little bit more massive than your surroundings, then you have a stronger force of gravity. So this region where there just happened by luck to be a little more stuff than average is a region where gravity is stronger. But if gravity is stronger there, what it means is that region is going to be more effective at pulling in gas from its surroundings. So this spot, which happened to start off having a little more stuff than average, is more massive, it has stronger gravity, and so it pulls more stuff from its surroundings in. And so it's a runaway process. The regions that initially have more stuff are the regions with stronger gravity that pull more stuff in, so they get more massive, so they have stronger gravity, so they pull more gas in, so they become more massive. And you can see that this is a positive feedback loop, analogous to the positive feedback loops you talked about in section this week. And so as time goes on, this tiny difference from one region to another gets amplified. The differences get bigger and bigger as time goes on. And so what started off as a small difference in how much stuff there is from one region to another gets bigger and bigger as time goes on. And so really, the only condition for this process to get going, is that there be a region where there's a little more stuff to start out with, and that seems like it'll always be true. There's differences from place to place. And that in this region where there's a little more stuff than average initially, the internal strength is low so that it doesn't resist collapsing due to gravity. And as long as that's true, this gravitational runaway process will operate. and it'll kind of make the rich get richer. The regions that start off with more stuff get richer and richer and richer and end up with more stuff. Yep?
What areas would have a high?
So a region that would have a high internal strength, for instance, would be a region that happened to be really hot. If you're hotter, you have higher pressure, you push out more. And so a region that's hot will actually resist this process better than a region that's cold. Great question. Okay, so what I want to do now is I want to show you a computer simulation of how this gravitational runaway process works. This is the same simulation that you saw in section. That's actually intentional, right? I think this really drives home a lot of the key ideas, so I want to show it again and gives you, I think, a good feel of how this gravitational runaway process works. So what this is a calculation on a computer where we solve the laws of physics as we know them for a big ball of gas that initially is about a few light years across, and the mass of this ball of gas initially is about 1,000 times the mass of our sun. The physics in here is things like gravity, as Newton taught us, cooling, the force due to pressure, high pressure pushing on low pressure, things like that. So this has a lot of different physics that captures a lot of these ideas that we've tried to describe over last lecture and just now. And so the simulation, what the simulation starts with is a little random. It didn't have to be a nice sphere. They could have started with something less perfectly spherical, and you'd actually get a similar result. So the initial beginning state is a little arbitrary. What you end up with, though, is kind of robust. And time will march on, shown up here as the simulation goes. And the color tells you basically how much stuff there is. White or dark yellow is lots of stuff there. And so you can see immediately, you go from a smooth beginning. You can see in the beginning that there are tiny differences in color. That represents tiny differences in density from one place to another. And as time goes on, those differences get amplified. Certain regions end up much denser with a lot more stuff than their surroundings. So this region is growing, this region is growing, this region is kind of losing out in this competition. And now the color bar is changing to isolate a really dense region. The flashing is an artifact of the movie. Sorry about that. So now we're just looking, rotating, zooming in. This is a very dense region. Now you'll actually be able to really visualize how this is pulling stuff in. This region here, stuff is falling in. The gravity of this is pulling stuff in. The little white dots now are actually individual locations where stars have formed in this simulation. You can now, as time goes on, you can really start to see how, as stuff falls in, it doesn't fall directly into the center. Instead, it starts to rotate and form one of these swirling disks, illustrated here. So at the center of this disk is a newly formed star, and in this disk is where the planets around that newly formed star are going to form. And you can see it's a chaotic process. Actually, disks slam into each other, stars slam into each other. In the early stages of stars and planets forming, it's actually a relatively dynamic, violent process. Yep?
So all those little stars that you're shooting out,
Yep.
each one of those stars have the ability to become a solar system.
Yeah, the question is, does each of those kind of white points later on in the movie, each of those represents a star that will have one of these rotating disks around it, and so each of those white points has the potential of becoming a solar system. And if you move Zor in, and in this calculation, you can't zoom all the way in and see the actual planets forming. And the way to think about it, it starts off with about 1,000 times the mass of our sun. A typical star in our galaxy weighs a little bit less than the mass of the sun, maybe about 1/3 of the mass of the sun. So there's the potential in this cloud to form thousands of typical stars like the sun. Yep? Yeah, so great question. So sometimes you'll notice what happens is that actually as stars kind of pass near each other, they give each other such a big gravitational pull that they can send the star kind of flinging off from where it was. And this is similar to the idea I mentioned that when our galaxy collides with Andromeda, our neighbor, in 5 billion years, there's some chance that the solar system is going to be kicked out into Andromeda by gravity during that collision. It's a similar idea. So we actually think, and we'll talk about this towards the end of the class, that in our galaxy there are billions of free-floating planets not actually orbiting around a star. And we think the way those formed is in these violent collisions that kind of kicked planets flying off like you can see in this movie. Yep? Yeah, so the reason for why they spin, I'll get to in just a second. Great question. That's exactly what we're going to get to next. Any other questions? Yep?
So if it says log column density, does that mean that a lot of these stars are like one is like way deeper than the next and they might not actually be as close as they look?
Yeah, good question. So the question is, what exactly is the color scale? And also the question was getting at, this is really a three-dimensional sphere-like thing. And so what this image has done is it's basically collapsed that three-dimensional thing into just a two-dimensional image. And so some of the stars that look close to each other are actually not physically close to each other. They can be kind of projected close to each other. So one can be here, one can be back here. But when you project it onto a single plane, they look close to each other. So there is some projection effect in the image. That's exactly right. Yep.
Are these gas clouds more commonly found in space between galaxies or
Excellent question. Are the gas clouds found primarily in galaxies or primarily outside of galaxies? So there's two answers to that. One answer is that most of the gas in the universe is not inside galaxies, it's outside galaxies. The problem is that the gas outside galaxies is incredibly tenuous. It's more like 1 atom per cubic meter, right? So this big a region has one tiny little atom of hydrogen. And so that is so tenuous that it doesn't form stars. So stars form where the gas is crammed together a little more, which is inside galaxies. Great question. Okay. So I want to get back to now this question about rotation. Why is it spinning? And you can again see that nicely in the movie, especially starting about here. And so what you'll notice is that the gas pulls in by gravity. It doesn't fall directly onto the star. And the reason for that is just the chances that it falls directly onto the star are very low. It's more likely that it's not heading exactly towards the star, but it's heading a little bit off at the side. And so what happens then is as it goes towards the star, it starts to rotate around the star rather than falling directly into the star. And as it falls towards the star, it starts rotating faster and faster and faster. And the analogy, the analogy is the kind of ice skater analogy that you've probably seen in high school physics, which is that if you imagine, right, the ice skater in the Olympics, as they pull in their arms to do the triple luge, Piro, blah, whatever, right, that move, as they pull in their arms when they're spinning, they actually start to rotate faster. And in physics, the reason for this is due to something called conservation of angular momentum. Just if you are interested and have heard about it, that's the reason. That's not going to be critical for what we're talking about. I just want to appeal to your intuition that if you're spinning around and you pull your arms in, what that means is the mass moves into smaller distances. You actually start to spin faster. And that's what's happening in the newly forming solar system, is that as the mass gets closer to the newly forming star, it starts to spin faster and faster and faster. And at some point, it becomes like the Earth going around the solar system, where the gravity of the sun on the Earth doesn't cause the Earth to fly into the sun. It just causes the Earth to orbit around the sun. Exactly the same thing is happening here. As you spiral in, you spin faster. At some point, your rotation becomes exactly what is required to keep you in a nice, happy orbit around the star. And that's this phase when a disk, a rotating disk, has formed around the newly formed star. So there was a question? Yep. Yes, excellent question. So what I've told you here actually is true independent of whether this is a star, whether it's something more exotic like a black hole. So when we think about how black holes gobble up stuff from their surroundings, it doesn't fall straight in. It kind of forms one of these rotating disks for exactly the same reason. Great question. Yes?
If this is the star and it's going around like this, but it comes in at the other side, why would it not go off?
Right. So you can have a cancellation where here stuff is coming in like this and wanting to spin like this. Some other time it might come in the opposite direction. Absolutely, that happens, no question. And so I think the fact, for instance, in our solar system that most things are rotating in the same direction is a statement that most of the gas in our solar system was acquired from gas coming in one particular direction. And that direction of the rotation of the gas then determined the direction of rotation of the planets around the sun. Okay, any other questions about the rotation? Yep. Yeah, so how do you get stars of different sizes? Some stars have a mass of the sun, some are 100 times bigger. And there we think it really depends on, in this cloud, there'll be some regions that are, so this region right here has a little bit more mass than this region over here. This is going to form a bigger star than this one right here. So you get a range of different initial masses that cause this runaway process, and that then affects the final mass of the star. Then there is a little bit, and exactly how important this is, we're still not 100% sure, of stars actually crashing into each other, building up the mass of stars. That also can play a role. Yep?
Is that the same reason that this would form a star instead of forming a black hole?
Right, so the reason this forms a star instead of forming a black hole is that as the gas at the very center collapses in on itself, at some point it gets so hot that it now has internal strength to oppose gravity, and it stops collapsing anymore. And that's why it's a star rather than a black hole. Yep. Yep. Yeah, so actually in a calculation, in a kind of situation, gas cloud like this, not all the disks will be in the same direction. So around a given star, there's kind of a well-defined direction, but different disks in this region will have different directions. Okay. Yep.
Are most of the objects in our solar system that aren't planets just like asteroids and comets and things rotating in the same direction?
Yeah, the question is, are most of the objects in the solar system, not the planets, but the asteroids and the comets and things like that, are they also rotating in the same direction as things are orbiting? And the answer to that is largely no, actually. And That's for a reason we'll get to towards the end, probably. Okay. So I want to ask you a question now. So get out your papers and think about this for a second. So you have to visualize, this is really asking you to visualize this process. So here's my sphere that's rotating. This is my little gas cloud that's forming a star and a solar system. Gravity is pointing in, but this thing is also rotating, and it's rotating in the direction defined by that right-hand rule. So the way to visualize it is it's rotating kind of like this. And my question for you is, as we just talked about, as it collapses, it starts to rotate faster and faster and faster. At some point, it's rotating so fast that gravity no longer actually pulls it in. Gravity just keeps it in that nice rotating orbit like the planets going around the sun. And so the question is, if I think about that as rotation stops the collapse, just like, again, the Earth doesn't fall into the sun, it just rotates around the sun. The question is, in what direction does rotation actually stop the gravitational pull from causing things to collapse? Is it in all directions in this sphere, or is it only in certain special directions? Maybe to the right in this picture, maybe to the left, maybe up, maybe you think down, maybe I left off the right answer. So this is, I would say this is actually a bit of a harder question than the questions we've had so far. So talk about this for a second. Try to visualize, again, this rotation process that leads to the formation of a disk. Does it halt the gravitational collapse in all directions or only in certain special directions? And if it's in certain special directions, which ones? And again, the key to thinking about this is to be able to visualize the direction that it's rotating in using this right-hand rule idea. Okay, so go ahead and put up your answers. Okay, so I see some reds, some blues, some whites, occasional green maybe. Okay, so the first thing I want you to think about here is that in the movie, rotation leads to the formation of a disk. A disk is an object where it's collapsed a lot in one set of directions and not so much in another set of directions. So all directions is problematic because rotation is leading to the formation of a disk where the collapse actually hasn't been stopped very well in certain directions. And so, in fact, the right answer here is both of these directions. And the way to visualize it is what this produces as time goes on is something like this. Seen from the side, this is going to be an object where gravity has not stopped things from collapsing in this direction. So it's rotating like this. So in the up and down direction, gravity is not opposed by rotation. Rotation opposes gravity only in the direction that rotation is going. So that's kind of this plane in the setup I have here. So in this setup, what you will form is a flattened disk or a flattened pancake that from the side looks like this, where rotation has stopped things in this direction from collapsing, but not stopped things from collapsing in that direction. Okay. So think about this some more. If you have additional questions about it, feel free to come up and ask us afterwards, or you can talk to each other about it. So we actually see these disks around newly forming stars. Actually have famous examples in the constellation Orion. So Orion was a hunter in Greek mythology, and this is Orion's belt. And a little bit below Orion's belt in the sky is what is called the Orion star-forming region. This is a cloud of gas that is actually one of the nearest, most well-studied regions where new stars are forming. And so if we now zoom in to specific locations in the Orion star-forming region, you see pictures like this. So what this is these are disks around newly formed stars where there's so much stuff in the disk that it's blocking the background light. And so you're seeing the disk actually in silhouette. It's shading out all of the background light, so the dark region traces out the size of the disk. For comparison, this is about the size of our solar system, out to order Neptune or so. And so these disks are similar in size, actually, to our solar system. The mass is, maybe a tenth of the mass of the sun down to a thousandth of the mass of the sun for different disks. And so we directly can take pictures of these locations where new stars are forming. And we think it's in these disks where the planets in our solar system and planets around other stars actually form. So we don't yet have pictures that are good enough to really see in exquisite detail planets in these disks around newly forming stars. We're just starting to get there with the technology, the telescope technology we have. So instead, I'm going to show you an artist's conception of what it might look like. So here is the newly formed star. This is this rotationally supported disk around the newly forming star. This is a gratuitous background galaxy. In this particular artist's conception, there's a big, very massive planet like Jupiter, which is so big that it's actually pushed all the gas around it away from it, clearing out this region where there isn't much gas due to the gravity of the planet orbiting around, pushing stuff away. We think that these disks around stars are the places where Jupiter, Uranus, etc., all the planets in the solar system form, because there's a well-defined sense of rotation in this disk. That's why the planets end up rotating around the star in basically the same way, the same direction. So the one real wrinkle to how the planets form out of this disk is you might think, based on everything I've told you, that the way that the planets form is that within this disk, there are some regions where there's a little bit more stuff than average. So gravity there is a little bit bigger. So that'll cause that region to collapse in on itself and form a planet. That would be kind of the natural extension of the story we already talked about. And it turns out that that's actually not the major way that planets form, or at least the way planets get going. And the reason is that these disks around stars are actually hot enough that they have enough internal strength that they try to resist that gravitational collapse. And we actually think then the way the planets form is by a process that's called a bottom-up process. It actually starts from incredibly tiny objects, little minuscule bits of gas and dust that build up over time to get bigger and bigger and bigger. So this is actually an example of the minute particle of dust that was the seed for the formation of the Earth. Okay, maybe not exactly the one that formed the Earth, but the general idea, the Earth, the process of the Earth forming started from stuff that is literally analogous to the tiny little dust balls and dust bunnies you see in your room when you haven't vacuumed for a while. And what is that? So in astronomical terms, we use dust to really just mean large molecule. So an atom, right, is just a single nucleus with a bunch of electrons going around. Molecules are a bunch of atoms held together by electric bonds. And dust is basically really big molecules. So this thing right here, the scale bar is, this is a few millionths of a meter in size. And the way we think that planets form is actually this very counterintuitive process that you wouldn't guess initially would be the way that planets form, but it actually starts with these small things, and as time goes on, as these small things run into each other, they build up bigger and bigger and bigger sized objects. So you start with these micron-sized large molecules. They collide with each other to build little pebbles. The pebbles collide with each other to build rocks. The rocks collide with each other to build asteroids. The asteroids collide with each other to build planets. Once the asteroids get big enough, a few kilometers in size, then their gravity starts to be important, and then they do kind of gravitationally pull in stuff from their surroundings. And that object is often called a planetesimal, like little planet, right? So that's the kind of rock when it's big enough that its gravity starts to pull in stuff from its surroundings. And so this is the essential way that we think that planets like the Earth formed. Start small, build up through collisions in time, building bigger and bigger rocks. Yep?
If it's putting stuff around it because its gravity is inside of pieces, what causes it to stop pulling in?
Great question. So what causes it to stop pulling in matter eventually? So this actually is intended to partially illustrate that schematically. So this is a kind of a cartoon of a newly formed star, and the left is early times, and then time is going on to the right. And here there's a bunch of rocks orbiting around, and as time goes on, those rocks collide with each other, building up bigger and bigger rocks like the planets. And then at the end, we're left with a few big rocks, we just happen to call those planets, orbiting around the star. And so what happens is at some point, the planet basically gobbles up everything near it in its orbit. And then it runs out of stuff that it can pull in, and that's the end of the kind of planet growing phase. So that really determines how big the planet gets, is how much stuff is there around it in the disk around the newly forming star. Great question. Yep? Yes. No, so this is the process that gets all planet formation going. What then happens for Jupiter and Uranus and stuff I'll get to in just a second. But this is actually Uranus and Jupiter and Neptune started, we think, probably, this is still a little uncertain, but started actually from a similar process. So at the center of Jupiter and Saturn and Uranus is actually an Earth-like rocky planet, surrounded by a bunch of gas. Yep.
This is also probably jumping ahead, but so like planet equals seems
Yes.
to have uniform composition. So how do you get something like the iron core?
Great question. I think Charles will talk more about that next week, but basically the idea is that as you form the Earth, these collisions of rocks that form the Earth actually make things very hot, and the rock actually melts, and so then it chemically differentiates with the heavy stuff sinking to the center, the iron sinking to the center. So it doesn't stay completely rock. It actually becomes effectively liquid, and then it can separate out. Excellent question. Yep.
Why is it not possible to actually share the same orbit? They have been on the opposite side of the
Yeah, in principle, you could have two planets on exactly the same orbit. The problem is if they're distant, so the idea is if you have two planets on opposite sides of the star, they go around with exactly the same orbital period, they never run into each other. The problem is that if they have slightly different distances from the star, that means they have slightly different orbital periods, and that means eventually they'll get near each other and one of them will kick the other one away. So that's what ends up happening. And so two planets on roughly the same orbit is unstable. One of them gets booted out. Okay. So that's the basic story of how we go from clouds of gas to stars by gravitational runaway, to disks, to planets in disks. And what I want to do now is talk a little bit about the difference between the inner planets and the outer planets, getting at this question that was asked a second ago. And in particular, what I want to get at is why are inner planets made of different stuff than outer planets? The inner planets are rocks, they're iron and oxygen and silicon. The outer planets are generally more massive and they're made of different stuff. They're actually made mostly of hydrogen and helium like the sun, and they're also made actually of a fair amount of ice. And the key to the difference between the inner and outer planets is roughly the following. Here's the sun. This is my schematic of the disk around the star. Close to the star, you get heated by the sunlight more than far from the star. So the regions close to the star are hotter than the regions far from the star. And it turns out that the region around 0 degrees centigrade, which is where water freezes, it's where you go from having solid ice. Actually, the pressures are so low you don't have liquid. You go from solid to gas directly. So out here, the temperatures are below 0 degrees centigrade, so water freezes. You have ices. In here, the temperatures are so high that you have gas rather than ice. And this region is often called the snow line or the frost line because it's where basically you start to condense out solid material. And the key point is what happens then. So out here, you have ice, you have water in solid form, and you also have metal in solid form, iron oxide, silicon, rocks, things like that. So out here, you have a lot more solids than you do in here. In here, your ices are in the form of gas. The only solids you have are kind of your more familiar rocks. And what that means is that in the outer part of the solar system, there's actually more basic building blocks for this process. Because you have icy rocks that have more mass in solid form in the outer part of the solar system. So out here, you have more of these building blocks for getting planet formation going. And so out here, you tend to more easily form planets that have a lot of ice in them and that are bigger because you have a larger amount of this solid material available to form planets. And I should say, everywhere in the newly forming solar system, most of the mass is actually in the form of gaseous hydrogen and helium. So most of the materials in gaseous form, the stuff that's in rocks is either just the kind of irons and silicon and stuff like that, or that plus ice. And these are the building blocks that get planet formation going. Hydrogen can be solid, but it's minus 260 degrees centigrade to get hydrogen to form a solid, and that doesn't exist anywhere in the newly forming solar system. So hydrogen is always in gaseous form. Yep. Right, great question. So what is the asteroid belt? So the asteroid belt is a region where we think actually planet formation failed. The reason is probably that it was so close to Jupiter that Jupiter's strong gravity kept things moving around really fast, and that inhibited the rocks from forming a planet, and we're just left with the asteroids at that location. So it probably will not form a planet. Yep.
The
Yeah, so I'll come back to that, this kind of atmosphere in just a second. So, yep.
But isn't there another asteroid belt beyond Pluto with the Kuiper belt?
Yeah, that's right. And yep.
Sure, I was just wondering why didn't that not form?
So the question is, there is actually another kind of basically asteroid belt that's out beyond Neptune. That's what Pluto is part of, called the Kuiper belt. And that is also a region where there were a lot of rocks that did form some planets. That's Neptune. It also formed big rocks. That's Pluto. And we'll talk more about exactly what that is and how it behaves a little bit later in the class. So the rocky planets in the inner part of the solar system are basically formed from this iron and silicon that was in solid form in the inner region where the solar system was hotter. The gravity, if you have a really big rock, then the gravity of the planet is able to hold on to an atmosphere of gas, at least of heavier elements like oxygen and nitrogen. But the Earth's gravity is not strong enough to hold on to the hydrogen and helium gas that was in the newly forming solar system. And that's why our atmosphere is mostly made not of hydrogen and helium, but instead oxygen and nitrogen. Mercury's gravity is weaker than the gravity of the Earth. Mercury wasn't even able to hold on to an oxygen and nitrogen atmosphere. It has essentially no atmosphere. So bigger rocks are able to hold on to some gaseous atmosphere. Smaller rocks don't have a gaseous atmosphere at all. Yep? Right. So for close-in planets, part of what happens is that the atmospheres get heated up so much that they do evaporate off the planet. Yes. So what about as we move to the outer part of the solar system? Uranus and Neptune are examples of what are called the ice giants. So they're actually, in some ways between Earth-like planets and Jupiter-like planets. They're made mostly of rock and ice. So they're made kind of like the Earth of mostly solids, but they just have the additional solids available in the outer part of the solar system where the ices were in solid rather than gaseous form. And I should emphasize, when I say ice here, it's not just water ice that you're familiar with. It's also other kinds of ices like ammonia, which is NH3. So other molecular compounds involving hydrogen can form ice in addition to H2O. And so that's kind of the content of Uranus and Neptune. Jupiter and Saturn are actually a little bit different. There's another wrinkle to their story. At the center of Jupiter and Saturn is basically a big Earth-like planet. So Jupiter and Saturn started forming in exactly the same way that the Earth and Uranus and Neptune forming, these rocks colliding with each other. So the center of Saturn we know better than the center of Jupiter for observational reasons I'm not going to get into, that at the center of Saturn is a rocky core that is between 10 and 20 times the mass of the Earth. But that is surrounded by mostly gas. So Jupiter and Saturn are little rocky planets at the center surrounded by mostly gas. And what happens is that as the rocky core that makes up Jupiter and Saturn gets bigger and bigger as things collide, at some point, when the rocky core is bigger than about 10 times the mass of the Earth, we think a new kind of gravitational runaway happens. What happens is the rocky core starts to pull in gas. As it pulls in gas, that makes the planet more massive, which makes its gravity stronger, which makes it pull in more mass, which leads to a runaway. And so you get a gravitational runaway forming Jupiter and Saturn, but only once you've already built up a rocky core that's about 10 times the mass of the Earth. And why you have to have that rocky core already is a little bit beyond the scope of the class. You're just going to have to trust me on that. that kind of planets like Jupiter and Saturn mostly form, not all of them we think, but most gas giant planets form in this way, build up a rocky core, and then you have a gravitational runaway process go on.
So do Neptune and Uranus have large atmospheres?
So Neptune, so the composition of Neptune and Uranus does vary with height. So in some sense, Neptune and Uranus it's almost all, the outer part is a big atmosphere. So they do have very extended atmospheres, but it's mostly still of this icy material, not just pure hydrogen and helium. And so what's actually special about Jupiter and Saturn is that their composition, mostly hydrogen and helium, better reflects what the solar system was actually made out of when the solar system formed. The solar system was mostly hydrogen and helium, plus a little bit, a few percent, of these rocks. The rocky planets formed just from those rocks, but the gas giants were able to gobble up the hydrogen and helium that represents the majority of the mass in the newly forming solar system. And in fact, the picture you should have of how Jupiter and Saturn formed is that in many ways, the formation of Jupiter and Saturn is actually analogous to the formation of the solar system itself. So here's the schematic diagram of the newly forming sun, surrounded by the disk out of which the planets are forming. Here is a hypothetical region where Saturn is forming, or Jupiter is forming. Zoom in to that region, and it actually looks kind of like a scaled-down version of the solar system forming. There's the planet at the center, gobbling up surrounding gas, in this rotating disk that is building up the mass of Jupiter. The moons of Jupiter are forming. So the big moons of Jupiter formed in a rotating disk around Jupiter, just like the planets formed in a rotating disk around the sun. It's very much an analogous process. Yep?
What determines whether or not, so if Jupiter is a bunch of helium and hydrogen as well, and so is the sun, what determines, one being sun with, nuclear, fusion and fission going on?
Yep, great question. So the question is, Jupiter and the sun are both basically balls of hydrogen and helium. One of them, the sun, undergoes nuclear fusion, shines really bright. One of them, Jupiter, doesn't. Why is there that difference? That's something we'll talk about a fair amount. And the answer turns out to be that Jupiter, as it was contracting, just never got hot enough for fusion to really get going before it developed enough internal strength to stop collapsing. And we'll talk a little bit more about why that is later. So you should now have some feel for why the solar system planets have the properties they do. And what I want to do in the last bit of the class is tell you a few of the consequences of the fact that the solar system formed in this bottom-up manner. It formed from small things slamming into each other to make bigger things. That fact about the solar system turns out to be extremely important, not only for explaining what we see in the solar system, like that there are asteroids and comets, but also for things like the evolution of life on Earth, extinction of the dinosaurs, etc. So the first big implication, the first big consequence of this bottom-up planet formation is actually the formation of the moon. We think the moon formed in the collision of a giant asteroid with the Earth. So this is an artist's conception of the young Earth, maybe 30 to 50 million years after the Earth formed, and it was slammed into by a huge object, about half the size of Mars is the best guess. And that collision ripped off material from the Earth, and out of the debris from that collision, the moon formed. And this object that slammed into the Earth, giving rise to the moon, is often called Theia, because Theia is the Greek goddess that gave birth to Selene, which is the moon god in Greek mythology. And so I'm going to show you a computer simulation of this process. So this is a computer simulation of the Earth being hit by the moon. In this particular calculation, the Earth is spinning pretty fast. That's why it's distorted. It's not a perfect sphere. That's a detail. Don't worry so much about that. So here's the simulation. Moon comes in. Now they're going to kind of illustrate by color the inner part of the Earth, the core as distinct from the outer part of the Earth. And the point is to illustrate to you the collision is so violent that it really goes all the way in towards the core and flings some of the material from the core out into the surrounding debris. And then the idea is that if we now stop this movie here, this collision only took about 10 hours. Okay? If we stop this movie, this is the Earth, and this is the debris created by the collision. This debris takes the form of a rotating disk around the Earth, and out of that rotating disk, the moon formed, much like the planets formed in the rotating disk around the sun. So the moon formed out of this debris, this disk of debris created in the collision. So that's the basic picture of how we think the moon formed. Yep. How long did it take to form the moon? I think tens of millions of years. Charles, do you remember? But I don't actually remember the exact time. Maybe less than that? So there is actually a real problem with the story I just told you. Question? Yeah? Yeah, Mars-sized is half Mars. In this slide, Mars-sized meant roughly the size of Mars. But in this particular calculation, it's more like half the size of Mars. We don't actually know, and so different people's calculations assume different things. But it's roughly that size. So there is I'm going to hold off on questions just because of time. So there is one problem with this story. If this is supposed to be where the moon formed, okay, so zoom forward. So here's the Earth, and there's the moon. How far away is the moon from the Earth now? On the scale of this picture, the moon is past Charles. So how do we go from the moon forming very close to the Earth, which is what we think happened actually, to the moon being way over there, 60 Earth radii away? This is actually an amazing story. We think it's actually due to tides. Tides raised on the Earth by the moon move the moon from where it was formed very close to the Earth to very far away. And so let me explain that to you, also explaining as we go what tides are. So this is my schematic diagram of the Earth and the moon. And when we've been talking about the force of gravity that the moon puts on the Earth, or that two objects pull on each other, we've really been talking about kind of the average gravitational force. So kind of the force that the moon puts on the center of the Earth, you can think of as the average gravitational pull that the Earth feels. But of course, this side of the Earth is closer to the moon, so it feels a somewhat stronger pull of gravity than the center of the Earth. This side of the Earth is further away from the moon, so it feels somewhat weaker force of gravity, because gravity gets weaker as you go further away. And so the gravity that the moon exerts on the Earth is actually not the same everywhere. It's different on different sides of the Earth. And that's the fundamental origin of the tides. And so the way you should think about it is that the Earth gets distorted in shape from being spherical to having this elongated shape, what we call the tidal bulge, due to the gravity of the Earth. And the idea is that this region over here is pulled towards the moon, and this region here, that's the opposite side of the Earth from the moon is kind of left behind relative to the center, because gravity is stronger at the center than on this side. And so that leads to this distortion where this side is kind of left behind, this side moves towards the Earth, so you get this symmetrical distortion. And this region that's closer to the moon is a region that would represent high tide. Okay? This region, it would represent low tide. The reason we have 2 high tides a day is that as the Earth rotates underneath this, one high tide when you're here, other high tide when you're here. The fact that it's symmetrical on both sides give you the 2 high tides and 2 low tides every day. So the tides, a kind of exaggerated view of what the system looks like would be something like the following. So this is the moon, this is the Earth. The blue is meant to represent the tidal bulge, the distortion in the shape of the Earth due to the tides. The distortion in shape is greatly exaggerated. And you notice that the distortion isn't pointing exactly towards the moon. That's also greatly, greatly exaggerated. But it is true that in general, the distorted shape of the Earth is not pointing exactly towards the moon. And that's for rather technical reasons having to do with friction in the Earth that I'm going to skip. So I'm a little nervous about time, so let me hold off on questions, and please come up afterwards with the questions. So in this picture, the Earth and the moon are both rotating counterclockwise, so rotating like this. What the arrows represent is that the gravity of the moon tugs on the bulge of the Earth. So the Earth, because of its distorted shape, the gravity of the moon pulls back on the Earth just a little bit. And if the Earth is rotating in this direction, but the gravity of the moon is pulling backwards in the opposite direction that the Earth is rotating, then what the moon does is it actually causes the Earth to slow down in its rotation. So the gravity of the moon tugging on the tidal bulge of the Earth causes the rotation of the Earth to slow down. Likewise, that rotation in physics, kind of sense of rotation, is conserved. So, and the fancy word for that is conservation of angular momentum. So the rotation of the Earth has to go somewhere, and where it actually goes is into the orbit of the moon. And so the moon gets a little bit of a push. So it actually gets a little bit of extra sense of rotation, which pushes the moon away from the Earth. The gravity of the Earth's tide back reacts on the moon, moving the moon away from the Earth. And so this process of tides acting back and forth between the moon and the Earth has caused over time the Earth's day to slow down, and it's caused the moon to move away from the Earth. It's pretty slow, so the day gets longer, right? You rotate more slowly means the day is longer. The day gets longer by about 2 milliseconds over a century, so it's not something you're going to notice. The moon moves away about 4 centimeters a year. That's the speed of the moon from the Earth. Again, hard to notice. But remember, we've had 4.5 billion years since the solar system formed. Over 4.5 billion years, the moon has moved from where it formed very close to the Earth to its current radius much, much, much further away. And the day has actually lengthened from several hours to the 24-hour day that we know and love today. We actually know directly, empirically, that this has happened, that the day has lengthened. And Charles is going to you can briefly describe how we know that by measurements of corals.
So it turns out that corals are a little bit like trees. They have growth rings in them. And so you can go back to corals in the fossil record, back to, say, 400 million years ago, and you can look at the daily growth rings as well as the yearly growth rings and estimate the time, the number of days in the year. And I'm going to leave my microphone, be fine if I do that. And so here is an old diagram from 1963, where paleontologists measured, for example, about 400 million years ago, that there are about 402 days in the year. And so in the Cambrian explosion of animals, there were many, many more days in the year than the 365 we have here. So we actually, in the fossil record, have measurements that capture this process that Elliot has been talking about.
And so remember, the year isn't changing. That's the time to orbit the sun. More days in a year means that the Earth was rotating faster in the past. It's been slowing down. Tides do something else. You may have heard that the moon, if you're on Earth and you look at the moon, you always see the same side of the moon. And the way we say that is the moon is locked. It's tidally locked so that as the moon orbits, it's rotating around its own axis in exactly the same amount of time that it's orbiting around the Earth, so that the same side of the moon is always facing the Earth. And that's due to the action of the tides of the Earth on the moon. So I want to mention a few other implications of this bottom-up process of solar system formation, things colliding into each other, making bigger things. We think actually that the water on Earth that's so critical for life, we don't really understand exactly where that came from. But one idea is that asteroids in the outer part of the solar system that had ice in them, because remember in the outer part of the solar system you had ice in addition to rocks, those asteroids may have actually brought, through collisions with the Earth, may have brought water to the Earth. So that may have actually played a critical role in one of the building blocks of life on Earth. I mentioned when we looked at the spin, the direction that planets are spinning about their own axis, that most of the planets spin in the same direction as they orbit. The exceptions to that are Venus, Uranus, and Pluto. Even the Earth has that 23-degree tilt of its spin axis relative to its orbital axis. And we actually think that that tilt of the Earth's axis and the huge tilt for Venus, Uranus, and Pluto is due to collisions. The collision that formed the moon, we think, tilted the Earth, giving us our seasons. Collisions of Venus with other big asteroids flipped completely its sense of rotation, ditto Uranus and Pluto. And so that's really shaped how these objects spin. Another question you can look at. So the last thing I wanted to emphasize is just that this process of things colliding with each other is, of course, still ongoing. This was the San Francisco Chronicle SF Gate website on Monday. Close call with an asteroid over the weekend raises concerns. Why does it raise concerns? Well, we might die. And so this process of things colliding with other things in the solar system is still ongoing. Here's a movie of the sun. So the sun is here. The sun is blocked by this disk because it's so bright. We block the light from the sun to see things around it. Does anybody see anything neat happening? These are two comets. Okay. Two comets flying into the sun, getting burned up in the atmosphere of the sun. The sun is, in fact, still gobbling up asteroids and comets from its surroundings. In 1994, so this is an image of Jupiter. This is Io, a moon of Jupiter. In 1994, a famous comet, now called Shoemaker-Levy 9, hit the surface of Jupiter, producing a big, bright splotch of light that we could see. That collision of the comet with Jupiter left these dark scars on Jupiter that lasted for months. And of course, the reason for this class that these collisions are particularly important is that if the comet or asteroid that collides with another planet is sufficiently big, it can have a drastic impact on the evolution of life on the planet. We think that has happened actually several times in the history of life on Earth, including the extinction of the dinosaurs and the rise of mammals and ultimately Homo sapiens 65 million years ago. And we'll talk about that a fair amount more towards the end of the class, and this also ties in with the demotion of Pluto and this thing called the Kuiper Belt in the outer part of the solar system. So now that we understand how the Earth formed, what Charles will do next time is start to tell you how the Earth actually functions and give you a history of the geological and biological processes operating on the Earth.